Hi, everyone. I'm Yang, and I'm a second-year PhD student at Stanford University. And today I'll be telling you about some very interesting algorithms, about some combinatorial objects called Hopsets and spanners, and their applications to some recent work on combinatorial graph algorithms. Cool. Before I get into any technical content, I'm just going to mention my history with the ICPC contest. So I participated in the ICPC World Finals 2018 for the MIT team in Beijing, and in the ICPC 2019 World Finals for Stanford in Porto. You might ask, why did the university change? Well, that's because I graduated from undergrad and started my PhD. And finally, I would like to thank ICPC for having me speak today, and also for cultivating my interest in problem solving, which has been really useful throughout my PhD. So some work I'm going to be talking about today is based on collaborations, which are very common in theoretical computer science research. And some of this work is joint work with Shiri Chechik, Arun Jampalapati, Omar Rodham, and my advisor, Aaron Sitford. So what this talk, what the outline is first I'm going to define what a Hopset is and its applications to the problem of parallel reachability. Then I'm going to define a spanner and how it can be used to give algorithms to approximate the girth in directed graphs. And finally, I'm just going to give an overview of some other areas of algorithmic research outside of the technical content of this talk that I personally know something about and I also find to be very interesting. Let's get started. To motivate Hopsets, I'm going to be talking about the reachability problem, which is basically just what it sounds like. You have a directed graph G and a source vertex S. And I just want to find what vertices S can reach in the graph. So this is just BFS basically. You have the vertex S. I'm just going to run a BFS to find everything it can reach. The interesting part though is we can study it in models other than the standard computation model. In particular, in this talk, I'm going to study the parallel model of computation. The parallel model of computation is very interesting because these days there's huge amounts of data, and you often want to process like large chunks of the data in parallel at the same time while still having a cost of runtime that's not really prohibitive. And why the reachability problem? Well, it's basically the simplest problem on graphs. So if we want to understand whether we can process directed graphs in parallel at all, it's very important that we can understand how to solve this reachability problem. And kind of on the other hand, the fact that we don't even understand how to do reachability in parallel optimally shows a lack of understanding in how to process directed graphs at all in parallel. So before 2017, here's basically what was known about this problem. The first algorithm, kind of the most obvious algorithm for parallel reachability is this parallel BFS algorithm. So the work of this algorithm is linear. Here, work refers to the total amount of computation done over all the parallel processors. Just like some overall parallel processors of how much work they did. And the depth of the parallel computation is the longest sequence of computations such that one has to happen right after the other. So if you implement BFS in parallel, the work is linear, exactly like normal BFS. And the depth is the graph diameter, basically the longest, shortest path in the graph. This is just because you can imagine building the BFS tree one layer at a time. And every single layer can be processed in parallel. So another algorithm you can use is parallel transitive closure based on matrix multiplication. Basically, you take large powers of the adjacency matrix, and that works efficiently if the matrix multiplication constant is small. So the depth here is really good, but the work is much more than linear, even for dense graphs. And there's additionally two algorithms of Spencer and Ullman Yannikakis that give trade-offs between the depth and the work. The important thing to notice about these results is that none of these results show that you can do parallel reachability in linear work, basically the amount of work that just simple BFS needs, but having sublinear depth, as in depth substantially less than n. In particular, imagine that the graph's a path of length n. Then the parallel BFS algorithm takes n parallel depth, because I'm going to start at the front and just, the BFS would just get one vertex at a time. So the depth would be n. So how can we improve over this? An idea is to use an object called Hopsets, and let me motivate that. So the first thing to notice is that parallel BFS uses m work, but the depth is d. Recall that this is because you can just build one layer of the BFS at a time, and each layer can be done in parallel. Unfortunately, the depth d can be all the way up to n, say in the case where the graph is a path. And a way to get around this is potentially, what if we can add m edges to the graph, so just maybe double the number of edges on the graph at most, but these edges don't affect the reachability structure, and additionally, we can significantly reduce the diameter. In other words, we're going to add edges from u to v, where you can already reach v and g, so that adding these edges doesn't affect the reachability structure, but maybe after adding these edges, the diameter's really gone down. At that point, we can just run parallel BFS and have an efficient parallel algorithm. And we're going to let a Hopset be like such a set of edges, basically a small set of edges, such that when I add them to the graph, they don't affect the reachability structure, but significantly reduce the diameter. And a shortcut edge is an edge in the Hopset. Hopsets have seen a lot of use not only in this problem, but also in similar problems such as approximate parallel shortest paths in both undirected and directed graphs, and also similar problems in distributed computation or other models of computation. So let me present a pretty simple algorithm for Hopsets. The result I'm presenting is due to Ullman and Yannikakis, where they prove that you can add n edges to a graph G and reduce the diameter to root n. So that means Hopsets that reduce the diameter to root n exist. The process is very simple. They're going to randomly pick root n log n random vertices from the set of vertices in G and call it S. Now for any two vertices in S, if you can reach V, I'm just going to add an edge, shortcut edge from U to V. So there's a most the number of elements square number of edges, which is n. And kind of here's like a illustration of the process. Say I initially wanted to find a path from the left purple vertex to the right purple vertex. Initially, the path is kind of long. I need to go through a lot of edges. But what if I randomly first picked these vertices in the graph and then built the corresponding Hopset given by the above process? I'm just checking for every pair of vertices, can one reach the other, and adding an edge if we can. So that's my Hopset made up of the blue shortcut edges. And now say I wanted to decide again whether the purple vertices can reach each other. Well, I can now just go through the Hopset edge, and now my path is much shorter. So I can implement the BFS more efficiently in parallel. They proved that you can implement this algorithm in total work m root n and depth root n. Notice that the depth is great. It's root n, substantially less than the trivial n bound, but the work is much more than linear. It's m root n. In fact, this is like the best combinatorial known construction. Like even ignoring how efficiently we can implement the algorithm, it's not known whether Hopsets can reduce the diameter of the graph to less than root n. On the other hand, there is a lower bound of n to the 1/6, but it would be very interesting to close this gap between root n and n to the 1/6, whether you can get kind of the tight answer for Hopsets. At this point, I'm going to talk about some recent progress on this problem, where it was actually shown that you can do linear work and sublinear depth for this parallel reachability problem. The first result in this direction was an amazing algorithm of Feynman, which I'm going to talk about later, where he shows that there's an algorithm that can build a Hopset with n edges and reduces the diameter to n to the 2/3. Here, the O tilde notation means up to logarithm factors. So O tilde n means n up to polylogarithmic factors. Additionally, this algorithm can be implemented in work M and depth n to the 2/3. So this is basically like a legitimate parallel reachability algorithm that has nearly linear work, and the depth is substantially less than n. In some follow-up work, two co-authors and I were able to actually further reduce the diameter to n to the 1/2 plus a little o of 1. So almost matching the combinatorial Hopset constructions basically in nearly linear time. How do these algorithms work? Well, that's what I'm going to tell you now. So for basically the rest of this section, I'm just going to talk about the main problem of, can we give a nearly linear time algorithm for constructing a Hopset? It's known basically in all cases that if you construct a Hopset, then you can get an efficient parallel algorithm out of it, even though kind of naively the Hopset construction might seem to not be implementable in parallel. This isn't like a formal reduction, but that's the intuition. So as a result, I'm basically going to focus on constructing a Hopset in linear time as a sequential algorithm. Also, we're going to ignore strongly connected components because in those parts of the graph, very efficient Hopsets exist. So I'm just going to assume the graph's a DAG. Feynman's algorithm now works as follows. Simply just going to pick a random vertex V, compute the descendants, the vertices that V can reach, and the ancestors, the vertices that can reach V. It's going to add an edge from every ancestor to the vertex V, and an edge from V to every single descendant. Those are all valid edges, clearly, that you can add as shortcut edges. And finally, the algorithm will recurse on the descendant set, the ancestor set, and the unrelated vertices. That's the whole algorithm. Now, you're probably wondering, why does this algorithm work at all? Just seems like I defined some random process and said it worked. I'll try to give you some intuition for why it works. To analyze this process, let's first fix a path in the graph. Now the goal is essentially to prove that from the start point of this path to the end point of this path, that the expected length will be at most, will be substantially less than n. Because that means that the start vertex of the path to the end vertex of the path, a short path can get there, which basically means we've built a Hopset. To analyze this, we're going to make 3 subsets of vertices depending on the path. We're going to define path descendants, path ancestors, and path bridges. A path descendant is a vertex that the path can reach. Basically, any vertex at the start of the path can reach. A path ancestor is any vertex that can reach the path. Basically, any vertex reachable, any vertex that can reach the end of the path. And a bridge is any vertex that is in the middle. It's reachable from the start and can reach the end. The first thing to notice is that if I shortcut from a bridge in Feynman's algorithm, the one described on the previous slide, then the path is immediately shortcut to length 2. This is because when I search, I'm going to add an edge from the start of the path to the bridge vertex, and then the bridge vertex to the end. And both those edges exist because of the bridge. Now the path is shortcut to length 2, which is amazing. That means we don't have any more work to do on the path. So what if we don't pick a bridge vertex? How can we still guarantee that this algorithm is making good progress? Think about what happens when you don't pick a bridge. Now we're going to recurse on 3 pieces. So the path will get split between multiple pieces, and then we'll recurse. To make this recursion procedure more formal, we're going to define a set of path-related vertices, which are vertices that are either path descendants, path ancestors, or bridges. Basically, I only drew path-related vertices here. You should imagine that the graph has several other vertices in it that might not have any relations to the path, but those don't matter because if I pick one of those vertices, the path's not really affected. Now to analyze this recursion process, the first thing to notice is that if my shortcut vertex I picked is a path ancestor or descendant, the path will get split into two pieces in the recursion. So the path gets split into two pieces, but the graph gets split into three pieces. So another thing to notice is that if my shortcutter is unrelated to the path, nothing happens. And finally, some ancestors or descendants become unrelated in the recursion problems. So for example, in this picture, the path got split into two pieces, the piece on the left and the piece on the bottom. Notice that in the piece on the right with three green vertices, there's no vertices in the path. So those vertices, the three green vertices, became unrelated to the path. So just to recap one more time, the overall result of the recursion is that the path got split into two pieces, but some vertices that used to be ancestors, descendants, or bridges are no longer that. The main lemma, which drives the analysis, is that the expected number of related vertices at the next level of recursion is at most 3/4 times the number of related vertices at the previous level of recursion. So in here, you can notice that the number of related vertices went down by 3 in the next level. The 3 green vertices on the right are no longer related. Using this key lemma, we can get an analysis pretty directly. So let's define f of x to be the expected shortcut length of a path where x vertices are related. The previous recursion shows that f of x is in most f of a plus f of b plus 2, where a plus b is in most 3/4 x. Here you should think that a is the number of vertices in one of the recursion pieces and b is the number of vertices in the other recursion piece. And because of the lemma, a plus b is in most 3/4 x. If you set a equals b equals 3/8 x, then you can solve and get f of x is approximately x to the 0.7707, which is already significantly less than x, which is kind of the naive bound. Also, x can be at most n, because at the beginning, there's at most n related vertices. Also, if you improve this analysis a bit, you can get an n to the 2/3 bound. But basically what this shows is that because x is the most n at the start, every path will be shortcut to length and most n to the 0.707, which is exactly what we wanted to prove. So this algorithm I've shown builds a Hopset that shortcuts every path to length n to the 0.707, and I mentioned that a more detailed analysis can show an n to the 2/3 bound. At this one, I'm going to briefly outline how to improve it to n to the 1/2. The high level idea is we're just going to pick more vertices to run a BFS from. Unfortunately, you can't do this naively. You need to do it with some, you need to do it in a more special way. Specifically, what we do is we exponentially increase the amount of vertices we're sampling at every level of recursion. So in the first level, we're going to sample k vertices, then k squared all the way up, and k something like log n. The main tricky parts of this proof is that we need to still prove the algorithm runs in linear time, even though we're sampling way more vertices at every level, and also proving that we get a better diameter bound given this sampling scheme. And I'm not going to have time to discuss those, but I would be happy to talk about them later if people are interested. So yeah. So that's an outline of how to get a diameter reduction to n to the 1/2 based on the previous algorithm. Just to wrap this up, as I mentioned, there's a lower bound of n to the 1/6 known if you need n edges. So can we improve this n to the 1/6 lower bound? Maybe push it all the way up to n to the 1/2, and that would show that Hopset-based approaches for this problem are basically tight. On the other hand, n to the 1/6 and n to the 1/2 are actually very far apart. Maybe that means we can do better than this n to the 1/2 bound. Additionally, maybe it's possible that you can give algorithms that don't use Hopsets that are still very good for this parallel reachability problem. And finally, it's known that some of these methods help extend to approximate shortest paths. But what about something like exact shortest paths? Can you use similar methods and get any sort of guarantees? Well, yeah. Well, that wraps up the first part of the talk. At this point, I'm going to transition to talking about spanners and approximation algorithms for the girth. So I'm going to start by defining the girth of a directed graph G. In a directed graph, we're going to let it have n vertices and m edges, and every edge has a positive length. So the girth we're going to define as the minimum length cycle in the graph. It's depicted here. Here the graph has a girth of 4 given by the purple cycle. The girth is a fundamental property, so it's very interesting to give algorithms to either compute it or approximate it. There's been more focus on approximation algorithms, which I'll explain why now. There's a result of Williams and Williams where they prove that if there's any algorithm that computes the girth exactly in less than n cubed time for a dense graph, then that actually means we can compute all pair shortest paths in less than n cubed time. And that's like a popular hardness conjecture, and is conjectured to be impossible. For this reason, there's been a lot of focus on approximation algorithms for the girth, specifically multiplicative approximations. Say like getting a 2 or 3, a constant approximation of the girth. An object that's very helpful in approximating the girth is an object called spanners. Those spanners are very much like Hopsets in that they're a combinatorial object that is very useful for distance problems on graphs, or problems that have to do with shortest paths, distances, reachability, things like that. So in undirected graphs, there's an algorithm known that gives a 2k-1 girth approximation in time mn to the 1 over k. So if I want a constant approximation, I can have my runtime be as close to linear as I want. An object that is often used in a lot of algorithms are spanners. And a spanner for G is a subgraph H of G such that the distance in G between two vertices U and V is the most the distance in H between U and V is the most C times the distance in G between U and V. So basically, H is a subgraph, but it approximates all distances up to a factor of C, while hopefully having less edges. So in this sense, spanners are like a slightly different kind of combinatorial object than Hopsets. Hopsets, we're trying to add edges to help us have more efficient algorithms, but spanners, we're trying to like reduce the number of edges so that our computation can run quicker. So for example, if you have this graph, you can build a 2-spanner by removing a significant number of edges from the graph. All distances are still preserved up to a factor of 2, but we significantly reduce the number of edges. It's known that every undirected graph has a 2k-1 spanner with n to the 1 plus 1 over k edges, and you can compute such spanners efficiently. Additionally, the existence bound, the n to the 1 plus 1 over k edges, is conjectured to be tight. And I'll give a proof of this result later in the talk. Notice that these results are very similar, and that's basically because girth approximation algorithms are often based around the algorithms for building spanners, or sometimes more directly use spanners even. Spanners are a subcase of another very popular area of research in graphs called sparsification or compression. The way you should think about it is this. Oftentimes, there's large graphs that we have to process for whatever reason. But when we're processing a graph, we often don't care about all properties of the graph. We only care about very specific properties of the graph. So for example, your goal can be, I want to reduce the number of edges in the graph, or maybe the number of vertices in the graph, while approximately maintaining the information that I care about computing on the graph. For example, spanners, they approximately maintain distances. So if I only care about distances in my graph and not any other quantities, then spanners would be a great object to use. On the other hand, the graph might be an electrical network we're trying to consider. And the object called spectral sparsifiers approximately maintain effective resistances in this graph. In another view, maybe the graph is only a specific subset of vertices that you care about, some hub vertices, and we only care about specific quantities on those vertices. Then it might be possible not only to reduce the number of edges in the graph, but maybe to significantly reduce the number of vertices in the graph while still maintaining whatever properties we want between the vertices that we deem hubs or something like that. So at this point, I'm going to discuss what's known about approximating the Girth and directed graphs. So very little was done until recently, until some work by some co-authors and I, where we prove the following results. We show that we can get a 3 approximation to the Girth and directed graphs in m root n time based on some tricky random sampling scheme. We also give a k log n approximation in mn to the 1 over k time. And this is based on some sort of recursion in ball growing. Finally, we're able to combine these algorithms and get a k log k approximation in mn to the 1 over k time. So this last algorithm shows that if I want to get a constant Girth approximation, I can have my runtime be arbitrarily close to linear, which almost matches the case in undirected graphs up to this factor of log k. For the remainder of this part, I'm basically just going to focus on the second point. I'm going to show how to get a k log n approximation via some recursive scheme and this very simple but powerful technique called ball growing. So what is ball growing? To illustrate ball growing, I'm going to give an algorithm that computes a 2k minus 1 spanner with n to the 1 plus 1 over k edges in unweighted undirected graphs. As a reminder, a spanner is a subgraph that maintains all the distances up to a multiplicative 2k minus 1. The high level idea behind ball growing is just I'm going to pick a vertex v and then run a BFS shortest path from v until I deem that I don't want to anymore, and I'm going to cut. I want to terminate the search, delete the vertices I've searched, and then continue on to the remainder of the graph. More precisely, we need to define the balls. So BVD, I'm going to let be the vertices u in the graph that are within distance d of v. So it's like the ball of radius d around v, basically. The algorithm I'm going to do to construct spanners is I'm just going to pick any v in the graph, and I'm going to find the smallest d such that the d plus first level is a most size n to the 1 over k times the dth level. And then I'm going to add a spanning tree to the d plus first level, delete the dth level, and that's just my algorithm. So here's the algorithm, just one more time. Basically, I'm just going to start at v. I'm going to start running a BFS from it until the d plus first level is not that much larger than the dth level, and then I'm going to stop. So as an illustration, let's say start at that vertex. That's the next level I would compute, and that's larger, so I'm going to go to it. I'm going to go to the next level. That's also substantially larger than the previous level. Go to it. And suddenly, now I have a very sparse growth. So I'm going to stop my search. I'm going to add a spanning tree, and then if I was to continue, I would delete the vertices that's currently circled, and then recurse in the remainder of the graph, which there isn't much left. So why does this give a spanner? At high level, the analysis, all we say is the ball growing procedure can't go for more than k levels, because if that inequality BVD plus 1 is the most n to the 1 over k times BVD, it can only be violated. It can only be violated at most k times. Otherwise, the kth level will be size n to the 1 over k to the power k is n. And you know that the graph has only n vertices, so that's impossible. And to give the edge bound, notice that the size of the d plus first ball is the most n to the 1 over k times size of the dth ball. Also, we're deleting the dth balls over and over again. So the sum of their sizes is at most n, because there's n vertices in the graph. Therefore, the total number of edges we add in the spanning trees is at most n times n to the 1 over k is n to the 1 plus 1 over k. So yeah, this shows that we can build a spanner with n to the 1 plus 1 over k edges and is quality 2k minus 1. Now let me switch gears to directed graphs and give some intuition for the k log n algorithm. Say that our goal is we're going to try to find a cycle of length r in the graph, directed cycle of length r in a directed graph. So let's fix a vertex v and let's compute the outballs of radius r, 2r, all the way to dr. Here an outball just means I'm going to start at v and run a shortest path up to distance r in the graph. The main observation driving the algorithm is that if the d plus first the outball of radius d plus 1r has no cycles of length r, then no vertices that are within distance dr of v can possibly be in a cycle of length r, which is the length of cycle we're searching for. This is just because if a vertex of distance at most dr from v has a cycle of length r, then all those vertices in the cycle have to be within the ball of radius d plus 1r. This gives us a simple algorithm. We're going to recurse on the ball v d plus 1r, then we're going to delete the vertices that are in bvdr and then recurse on the rest. Notice that these pieces actually might overlap, which is what makes it an interesting recursion. We're going to recurse on overlapping pieces. Now the idea will just be if the pieces don't overlap as much or have very small overlap, then the algorithm will run very fast. So we're just going to pick d to ensure the overlap is small, and this will give a k log n algorithm. More precisely, we're going to pick d so that the overlap is size of most 1 over k times the size of the smaller ball. In that case, if the overlap is size 1 over k, then the next recursion level will have size 1 plus 1 over k times the previous. And just by using something like the master theorem or reasoning about it, you pretty directly get that the total size of the bottom level is n to the 1 plus 1 over k, which shows the runtime bound. And finally, to get the quality bound, if every single level grew by size n by size 1 plus 1 over k, then in k log n levels, the size of the k log n ball will be greater than n because 1 plus 1 over k to the k log n is greater than n. So the ball growing procedure can last in most k log n levels, which gives our bound. Finally, how do you get k log n? Like, where do you get this improvement from log n to log n? The observation we're going to use is that if the ball of radius dr is small, then we can actually allow for the boundary to overlap more. We don't need this very tight 1 plus 1 over k overlap, because when the ball we're recursing on is very small, the recursion bottoms out really quickly. So we can afford to have more overlap. So the algorithm will be, at the first levels of the algorithm, grow the ball very quickly, but then slow down as it gets larger. And doing this analysis precisely will give a bound of k log n. I think this previous algorithm, at least to me, is a little mysterious, especially for the occurrence of this log n parameter. But here's a problem I think that would help understand that I don't know how to do, and I would be super interested in any sort of progress or ideas for it. The problem is prove or disprove that for a directed graph G with m edges and no cycle of length log n over epsilon, that you can remove epsilon m edges from G and make it a DAG. This is known to be true, actually, if you replace the length log n over epsilon with length log n log n over epsilon. So I think this explains the appearance of the log n in the previous algorithm. And I think any sort of progress on this would probably have implications for that algorithm and several other algorithms or approximation algorithms for problems in directed graphs. So that wraps up the second part. And finally, I'm just going to give an overview of several other areas of algorithmic research that I personally find very interesting. Another area I've worked in, or I work a lot in, is the areas of continuous optimization for graph algorithms. Kind of the goal of this area is whether we can use continuous methods such as gradient descent or something like interior point methods or SGD, any of the variations, to give provably efficient algorithms for combinatorial graph problems. So some very interesting results in this field. A super crazy result is that you can give 1 plus epsilon, like very accurate approximate maximum flows between two vertices S and T in linear time. So you should think, if I want to get the maximum flow in an undirected graph to within 1% accuracy, I can have an algorithm that runs in nearly linear time that achieves this. Also, you can get results such as very low depth, polylogarithmic depth, and nearly linear runtime parallel algorithms for approximate shortest paths in undirected graphs. And algorithms that run in m to the 4/3 time for maximum bipartite matching and maximum in unit maximum flow. This improves over like the more classical algorithms of m to the 1.5, known by like Tarjan, Dinick, Hopcroft, Karp, etc. And the first result that kind of kicked off this whole field of continuous optimization for graph problems is the result that you can solve this matrix system in a graph Laplacian, Lx equals b, in linear time. So if L is a matrix corresponding to the Laplacian of a graph, you can invert the matrix on a fixed vector in a linear time. And this is a very amazing result due to Spielman and Tang. Finally, some other directions that are popular these days. Theoretical foundations of ML. Any sort of directions here are things like whether you can give efficient algorithms for learning data provably. Another problem is whether you can build a model or explain formally why things like neural networks work, or more broadly explain why any of the phenomenon that we see in machine learning work so well. And other things are more even like concrete convex optimization, just understanding what problems at all we can solve efficiently. And I think all these directions are super interesting and could have large practical impact. So yeah, that's my talk. And I want to thank ICPC one more time for having me speak today.